Now let us see what the implications are on the large signal, that is total characteristics of the two port. Okay. What do we have now? We have y11 equals 0, y22 equals 0, y12 equals 0, and y21 should be as large as possible. Y21 should be large. Now, the large signal characteristics can be described by these four graphs, where one of the variables is on the x-axis and the other variable is fixed, or it is varied as a parameter. Now, these small signal parameters are the slopes of these characteristics. Okay. For instance, the slope of I1 versus V1 is y11, slope of I1 versus V2 is y12, slope of I2 versus V1 is y21, and slope of I2 versus V2 is y22. Okay. Now, what does it mean to have y11 equals 0? By the way, these are only around some operating point. You have to choose the operating point correctly, okay, because the total characteristics of the nonlinear device can be anything. It's around some operating point that we need to have these constraints. So, what does it mean to have y11 equal to 0? It means that these characteristics I1 versus V1 are flat around some operating point. Okay. So, let us say this is the operating point here, then that means that the slope of I1 versus V1 is 0. And similarly, because y12 is 0, the slope of I1 versus V2 is also 0. Now, V1 and V2 are the only variables. Okay. So, what does it mean here? Around some operating point, y11 is 0, that is the variation of I1 with V1 is negligible, it is 0. The variation of I1 versus V2 is also 0 because y12 is 0. So, this means that this current I1 is constant, that is it is independent of V1 and V2 around some operating point. Okay. So, that is what is implied by these two small signal parameters. Again, it has to be remembered that this needs to be true only around a certain operating point. It does not have to be true everywhere. If it is true around a certain operating point, we have to choose that operating point. And similarly, y21 is very large. So, what does it mean? The variation of I2 versus V1, the slope of I2 versus V1 has to be very large around some operating point. Okay, it has to be as steep as possible. And y22 is also 0. So, that means that I2 versus V2 that has a characteristic like that around the operating point. Okay. So, what it says is that I2 versus V1 has to be very steep, whereas I2 versus V2 has to be very shallow. That is, I2 should not depend on V2 at all around some operating point. I also said that basically these graphs are drawn, for instance, I2 versus V1 is drawn with V2 as a parameter. Okay. Now, because I2 does not change with V2, so essentially this characteristic I2 versus V1 should be independent of V2. Okay. Because clearly around this operating point we know that I2 is not changing with V2. On the other hand, for this graph I2 versus V2, V1 is a parameter, okay, and we know that I2 changes very sharply with V1 in order to have a very large Y21. Okay. So, if you draw a parametric plot here, so for a particular value of V1 you will have this, for another value of V1 you will have a very different current, okay, but it will still be flat, that is it will be independent of V2. So, if V1 is V1B, the current will be different, but the variation of I2 versus V2 will be flat, that is the slope will be 0. So, what we have done is to evaluate the constraints on small signal parameters and from that infer what the large signal parameters have to be. And these are good characteristics of amplifiers regardless of what device you build. For instance, if you are trying to invent a new device, you have to invent a device which follows these things in order to maximize the gain. Okay. Of course, instead of choosing Y parameters, you can choose some other parameters and try to maximize the gain according to that parameters, but the qualitative characteristics will be the same. Okay. Meaning these characteristics, these parameters 1, 1, 1, 2 and 2, 2 will be nearly 0 and the characteristic 2, 1 will be very sharply varying. So, all it means is that the second port must respond strongly to the first port and all other responses must be very small. Okay. Now, I hope this part is clear. You will actually see later that the real devices that we have like the MOS transistor or the bipolar transistor do conform to this in their idealized form. Okay. So, that is why we chose to go like this, but it also gives you a sort of generalization. You do not have to stick to bipolar transistors or MOS transistors. If any other device comes along, just by looking at the characteristics, you should be able to say if it will make a good amplifier device or not. Okay.